Okay, so this lecture will study the MOSFET current models. A model as applied to electronic circuits and transistors and all that refers to a set of mathematical equations that describe the behavior of a transistor in our case. So what we'll study in this lecture is equations that describe the current, the drain current of a MOSFET as a function of the voltages applied. So we are going to do a quick derivation of the simple MOS current equation. I think you are all familiar with this equation, but we'll do a quick derivation. Again, as I had said last time, if you don't understand most of this, it does not matter, because we are really just going to use the final equation that we derive. We'll not be worried about the derivation of the equation after this lecture, but it is good to know. Okay, so this is the coordinate system. Some of this I had shown in the previous lectures. So you have a source and a drain and an oxide and a gate, and this I have shown the third dimension. So this is the width of the gate, which is in the z-axis, and along the channel is the y-axis. Perpendicular to the channel, going deeper into the substrate, is the x-axis. As we had defined last time, V is the voltage caused by the drain voltage. Alright, V is the voltage caused only by the drain voltage along the channel. Okay, and so we have a gate voltage applied, we have a drain voltage applied. For now, we'll assume that the source and body are grounded. Alright, so let us do the derivation. So I think you are all familiar with this equation, that the current density, electron current density in any material can be written as sigma times the electric field, where sigma is the conductivity. And in a semiconductor, the conductivity can be written as Q mu n, where Q is the electron charge, mu is the mobility, and n is the electron density in per unit volume. Alright, so Q mu n, E is the electric field. E can be written as minus dV dy, where V is the electrostatic potential. So I assume you are all familiar with this equation. So this is a starting point. We say, okay, I want to find the current, which is the integral of the current density, integrated over the cross section of the current flow. We say ID is equal to minus J and W dx. Why minus? Because this is an electron current. So you put a minus in front, because the current flow is has a negative sign with respect to the electron flow. So we say integral J, and W is the third dimension, dx is the depth, right? So you go back here. So we'll have an inversion layer here, and this is the direction of current flow is in the y direction. So we integrate the current density across a cross section, that is W and X. X is the vertical direction. So it's a W times X. W is a constant, it comes out. So we substitute for Jn and we take out mu n, assuming that it is a constant. dV dy comes out, because dV dy we'll assume is not a function of x. It depends only on y, the lateral direction, not on the vertical direction. And we keep the q inside, so this is the integral q n dx. Q n dx is actually nothing but the electron charge density, okay, multiplied by q. So that is the charge density integrated over the depth. So that is in fact the inversion layer charge at any y. Alright, so ID becomes W mu n dV dy Q inversion, the inversion layer charge. Okay. Now we invoke Gauss's law, which we had seen in the last lecture. So it is in some, as we had seen last time, it is Q equal to CV, slightly complex Q equal to CV. So is a Q is the total semiconductor charge is equal to the oxide capacitance into VGS minus psi s. So QS is the charge per unit area. Cox is the charge per unit capacitance per unit area. Gate source voltage minus the potential at the surface of the semiconductor. So VGS minus psi s. Alright, and as we saw last time, the semiconductor charge has two components, the inversion charge and the depletion charge. This is fixed, this cannot move, this is the acceptor ion charge, so we separate them out. Q depletion does not contribute anything to the current because these charges cannot move. Alright, so that is QS, Cox is oxide capacitance, VGS is a gate source voltage. Okay. This is an important equation which we will not discuss. In strong inversion, the surface potential can be written as 2 phi f plus Vy. 2 phi f, if you recall, is caused by the gate voltage. So if there is no drain voltage applied, the surface potential is 2 phi f. When a drain voltage is applied, an additional potential is caused by the drain voltage, which we represent as Vy. Now this equation is called the gradual channel approximation in MOSFET physics theory because this 2 phi f is caused by a vertical field, this Vy is caused by a horizontal field, and we are saying this is an approximate equation because we are saying that these could be written separately as the sum of two independent quantities. If you actually want to find the electrostatic potential at the surface of the semiconductor, you have to solve a two-dimensional Poisson's equation. It is very messy, it is very complicated, it actually cannot be solved. So this is an approximation that has been used for like 70 years, I think, maybe 65 years. Alright, so this is the equation we'll use. So what we are doing now is psi s will substitute here, QS will substitute here, and so we'll get Q inversion plus Q depletion equal to Cox VGS minus 2 phi f minus Vy. We want to find Q inversion because that is what goes into the current equation here. So we take the Q depletion on the other side and we take it inside the bracket, so it gets divided by Cox. So you get Q inversion equal to Cox into VGS minus this minus Vy. Now this, if you recall from last time, is the threshold voltage. This we had defined or found this to be the threshold voltage. In fact, one could say that Vt was defined from this derivation. Alright, we came to it from a very different path, but one could say that it came from here also. It doesn't matter anyway. So we get Q inversion equal to Cox into VGS minus Vt minus Vy. So we substitute this in the current equation here. So we get this, and then there is a dV dy, right? There is a varying with y, v varies with y. So then what we do is we integrate id from y equal to 0 to y equal to L along the length of the channel. So that is the left hand side. Right hand side, W mu and Cox comes out, and we'll get this dV dy on the right hand side. id of course is constant with y. id cannot change with y, otherwise current continuity will not be maintained. So this integral simply becomes id times L. L is the length, and on the right hand side we say at y equal to 0 the voltage is 0, that is at the source end. At y equal to L, which is at drain end, the voltage is VDS. So our limits become 0 to VDS, and then we integrate this out, and that is a very simple integral, and we get this, which is an equation I assume you are familiar with. So this is the simplest mathematical model for the drain current of a MOSFET. Alright, ID equal to mu 1 Cox W by L, VGS minus VT minus VDS by 2 into VDS. Most of you are familiar. If you are not, you must get familiar with this equation. This is one of probably 4 equations that you have to kind of memorize this semester. All right, this you have to know this equation just the way you know V is equal to I times R for a resistor. For a MOSFET, you must know this equation. All right, this equation we derived assuming that there was an inversion layer present throughout the channel, and that region is called the triode region before pinch off occurs. So that is this condition, and we have seen kind of seen this condition, but formally let us state it that this equation is for before pinch off occurs, for when the channel is existing throughout, the inversion layer is existing throughout the channel, and the condition for that is that VGS minus VT must be greater than or equal to VDS. At VGS minus VT equal to VDS, the channel pinches off at the drain end, and once it pinches off, as we saw in the first lecture, the current becomes constant. So let us find an equation for the current once the channel pinches off, and we say that that is a saturation region. So what we do is we substitute VDS equal to VGS minus VT in this equation to find the saturation current. So VDS equal to VGS minus VT, VGS minus VT. So this is VGS minus VT minus VGS minus VT divided by 2, which is VGS minus VT divided by 2 into VGS minus VT. So we get this equation by 2. So this is the drain current in saturation for an NMOS transistor, mu and Cox W by 2L. Please remember this 2. I have actually this bad tendency even after all these years to keep forgetting the 2 half the time. For me it's okay, but you cannot forget this when you are solving problems in exams. You are not allowed to forget. Alright, so this is the drain current equation in saturation. Alright, so let us summarize. So this is, as I said, this is the simplest possible MOSFET current equation, set of equations with the simplest model. And so what we derived were these two equations. In the triode region, this is a drain current, and it is this equation is valid for this condition. In saturation, this is the equation, it is valid for this condition when VGS minus VT is less than or equal to VDS. Of course, there is the other region which we have seen in the first lecture. If VGS is less than VT, we will assume that the current is 0. Again, this is a simple model. In the simple model, we will assume that the drain current is 0 when the gate source voltage is less than the threshold voltage. So there is one off region, there are two. If VGS is greater than VT, we have either triode or saturation. Alright. Just a remark about the condition. So we said that for saturation, VGS minus VT must be less than or equal to VDS, or VDS must be greater than VGS minus VT. Now this can be written if we write VGS as VG minus VS, VDS as VD minus VS, and then the VS will cancel. So we'll get VG minus VT less than or equal to VD. So this is the saturation region condition. It is important to realize that whether a MOSFET is in saturation or not does not depend on the source voltage at all. It depends only on the gate drain voltages and the threshold voltage. Alright, so if I want to determine, and we'll do this all the time once we start looking at circuits, if we want to determine if the transistor is in saturation or not, all we need to do is look at the gate voltage and the drain voltage. The source voltage is irrelevant for this condition. Alright. Okay, here are some numbers which are good to have a feel for. So that there was this mu and Cox, right? For in the MOSFET equation, the current equation. The mu1 is the mobility of mobility of electrons in silicon, and the mobility varies from about 200 to 1200 centimeter squared per volt second. In a high quality bulk silicon, the mobility is about 1200, and by high quality I mean where there are very few impurities in the silicon, and it is bulk silicon. Near the surface or interface, the silicon dioxide interface, which is where current flows in a MOSFET, the mobility is much lower, okay, because an interface creates a lot of impurities, and impurities mean that there is much more scattering and collisions, and so the mobility becomes smaller. So for MOSFETs, the mobility is more like 200 to 400. In bulk silicon, it can go up to 1200. Okay, so if we take the oxide thickness as 4 nanometers, which is typical of 180 nanometer CMOS technology, which is what we will be using in all our in all your simulations and designs. 4 nanometer is 40 angstroms. Then we can find the oxide capacitance per unit area as epsilon 0 into epsilon ox. The oxide dielectric permittivity is 3.9. Epsilon 0 is this much in farad per centimeter. Alright, minus 12 for meter, minus 14 for centimeter. Epsilon 0, epsilon ox by T ox, so T ox is this in centimeter, and so we get 8.6 femtofarads per micrometer squared if you find these number. Femto is 10 raised to minus 15. Alright, so the oxide capacitance of this 180 nanometer technology is of the order of about 9 femtofarad per micrometer squared. And then mu n Cox, so we multiply mu n and Cox, is of the order of 170 to 1000 microamp per volt squared. So these are the dimensions of mu n Cox, microamp current per voltage squared. If we take W equal to 1, L equal to 1 micrometer, then the total gate capacitance, which is the oxide capacitance per unit area into W into L, is 8.6 femtofarads. So these are typical capacitances for small sized MOSFETs, alright, of a few femtofarads. Of course, our MOSFETs in our amplifiers often will be much larger in size, so we shall see. Okay, here are the set of PMOS current equations, alright. We will not derive them, they are basically the same except that all the signs are reversed, alright. So because we will be using PMOSs as much as NMOSs. So by the way, so this is, I didn't show you this, I didn't mention the symbol, but I should go back and so this is a symbol for a MOSFET we will be using. There are 2-3 different symbols if you look at textbooks on MOSFET circuits. This is the one we'll use. This is what Razavi also uses. The arrow pointing outward is an NMOS, and that arrowed terminal is the source, the other terminal is the drain. For a PMOS, the arrow goes into the MOSFET, and that is the source terminal, and the non-arrow terminal is the drain. This is the gate. Usually, just by convention, MOSFETs and transistors are drawn on paper such that currents flow down, vertically they flow down. So usually, not always, but most of the time, a PMOS will be shown with the source above and drain below, because in a PMOS the current flows from the source to the drain. In an NMOS, current flows from drain to source, alright, because electrons flow from source to drain. Okay, so for a PMOS, if the source gate voltage is less than or equal to the mod of the threshold voltage, then the transistor is off. Alright, the threshold voltage of a PMOS is negative, alright, because the PMOS has an N-type substrate and you want to attract holes to the surface to form the inversion layer, and to attract holes you must apply a negative voltage at the gate. So the gate voltage has to be negative, and so the threshold voltage is negative. And everything is measured with respect to the source. So the source gate will be positive. All right, gate is negative with respect to the source. So source gate will be positive. Okay. On regions for triode, source gate is greater than Vt while this is on. Within it, triode is ID mu p Cox W by L, same as the NMOS. VSG minus mod Vt minus VSD by 2 into VST. And the condition is VSG minus mod Vt greater than or equal to VSD, which can be written as this if we remove the S, the source terminal. Alright, and similarly for saturation, VSG minus mod Vt the whole squared and 2L. Alright, so this is the simple MOSFET model. I keep saying simple because this model does not include a large number of physical effects. Okay, let me do this quickly. So the whole mobility in a silicon is smaller than the electron mobility. The typical numbers are 70 to 500. The oxide capacitance will be the same whether it's an NMOS or a PMOS, because the gate oxide thickness is the same. Mu p Cox is 60 to 400 microamp per volt square. Okay. Alright. As I said, this simple model does not include a large number of physical effects that are present in a real MOSFET. So here is a list of some for an NMOS. So the derivation that we just went through for this current, we had taken mu1 out of the integral, if you remember, which assumed that mu1 was a constant. Now it turns out that mu1 is actually not a constant. The mobility of electrons actually varies as the gate voltage varies. In fact, as the gate voltage increases and as the drain voltage increases, the mobility decreases. We will see this briefly in a couple of lectures' time. It turns out that W, the width of the MOSFET, is actually not a constant, and it is not, well, when I say uniform, so W is the width of the gate below which is the oxide, but the oxide thickness varies at the ends of the MOSFET, and this is called the bird's beak effect. We will not study this. Just know that there is something called the bird's beak effect, which makes W not actually W, but W plus some delta W. The channel length is a function of doping, it's a function of dimensions, it's the function of the source drain overlap with gate. Okay, let me quickly talk about this. So here we define the channel length as the edge of the source body junction to the edge of the drain body junction. All right, but this is really incorrect actually, because first of all, to begin with, there is a depletion layer. There is a source body depletion layer, drain body depletion layer, and that the extent of the depletion layer affects the definition of this length from this here to here. That length varies. If the substrate doping is higher, the depletion layer is narrower. That affects the definition of the channel length. All right. What else? The other thing is this N plus I have drawn exactly aligned. This gate edge and the N plus edge are exactly aligned. In real life, they are never aligned. The N plus actually goes a little inside. So the N plus will be actually like this. It has to be like that. So there is an overlap. There is a source gate overlap. So that reduces the channel length. So all these things affect the actual channel length And so a good model will take into account, and L channel length of course directly affects the drain current. So the actual channel length is called an an effective channel length, as opposed to just an L that we have defined. Okay. The threshold voltage is also not a constant. The threshold voltage varies with the gate voltage, drain voltage, length and W. Some of this we'll see later, some of it we'll not see. As I said, we assumed what is called as a gradual channel approximation in deriving this equation. That approximation was valid when the channel lengths were very long. They were called long channel MOSFETs, like 5 micrometers, 10 micrometers. This equation was very good. Nowadays, channel lengths are 180 nanometers, 20 nanometers, 10 nanometers. At these channel lengths, that gradual channel approximation breaks down completely. And so this whole derivation of this equation actually breaks down. And therefore this equation is very, very inaccurate. Alright. As we had seen in the first lecture, currents do flow in the MOSFET even for the gate source voltage less than Vt, and that is called as subthreshold conduction. And this list is actually a very small list of the actual number of effects, physical effects that occur in a MOSFET. And a good model, a good mathematical equation must include all these effects. And why do we need a good model? Because we use good models to describe the current voltage characteristic of transistors in designing circuits. This course is about designing circuits. And when we are designing circuits, we need to know how the current varies with the voltages. If we don't know how the current varies, there is no way we can design a circuit with that transistor. And if our knowledge of the current variation is very, very inaccurate, then our designs will be very inaccurate. Therefore, we need accurate models, mathematical models, to describe how the current of a MOSFET varies with the voltages applied, gate source, drain source voltages applied to that transistor. Alright. Okay. Having said that, so there are actually many different MOSFET models that are existing in the world. In fact, every large industry that designs chips and that manufactures circuits has their own MOSFET model. It is so important that like Intel and Analog Devices and Samsung, they'll all have their own MOSFET model. Because it is so important to have an accurate MOSFET model, and they guard it very closely. They will not tell us what their model is, because the derivation of that model is critical to design, and they don't want to reveal anything that is critical about what they are doing. Fortunately, the University of Berkeley, there is a team that has been working on developing better and better MOSFET models. As technology progresses and shrinks, more and more physical effects have to be taken into account. So Berkeley has been working on developing better and better models as technology progresses. And their model is called BSIM. I don't even know what BSIM stands for. It doesn't matter. And so there are many versions of the BSIM model that have come out of Berkeley. The one that we will use is called BSIM 3v3, and it's a reasonably stable, accurate model for bulk MOSFETs. All right. Now the MOSFETs are also many different types. There is the silicon insulator, and then there is a double gate, and then there is a FinFET, and all of these have to have their own models. This course is about bulk MOSFETs, and so we will be using the BSIM 3v3 model for the bulk MOSFET for all our SPICE based designs. And SPICE, the version of SPICE we will be using called LT SPICE, has this model incorporated in it. We will not have to Okay. 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 Let me show you something. Some equations. All right. So this top equation is the threshold voltage equation we had derived last time. Uh, hopefully you will remember. All right. So this is the simple threshold voltage equation. Just below it, and I've copy pasted this from the BSIM3 manual. This is the BSIM3 threshold voltage equation. All right. I don't expect you to know anything about this equation except the fact that it is very big, right? And it has a large number of what are called as parameters. All right, this dVt0, dVt1w, LTW, all these are parameters. So the BSIM3 model, okay, so this is the threshold voltage. Similarly, this is the BSIM3 drain current equation. All right, this is the drain current equation, and this current equation is valid in triode, in saturation, even in subthreshold. All right, and each of these terms have very big expressions which I have not even included here. I have just included an expression for VA SAT, which is here. So the IDS has a VA is here, there is a VA SAT is this, VACLM is this, just to show you. In fact, if you were to write out the expressions for each of these terms, this will fill about 2.5 pages. All right. So the BSIM3 model for the drain current of a MOSFET is very complicated. It is complicated because the MOSFET is a very complicated device and it has a large number of physical effects that must be incorporated. All right. So this is a model we'll use. We will not worry about the equations. SPICE will worry about it. The BSIM3 model has a large number of parameters. So as I said, this, let us see, ESAT, L effective, VDSAT, A bulk, PCLM, all these are parameters. The BSIM3 model has about, I don't know, some 80-90 parameters. I will give you a list of these parameters. So you don't have to do anything. When you run SPICE and you are simulating circuits in SPICE, you will simply use that set of parameters to simulate your circuits. All right. When we are designing things on paper by our hand, which we will do for most of the circuits we study, we'll analyze circuits on paper and we'll see why we need to analyze later. But when we analyze them on paper, we will use our simple drain current model that we derived in this lecture. When we do simulations in SPICE, we will use the BSIM3 model. All right, and we'll discuss in brief how to correlate these two models also as we go along. All right, so that is the end of this lecture. Actually, no, this is not right. Okay, the next lecture we'll talk about we'll plot some IV characteristics of MOSFETs.